Hello, how is everybody? Yeah, I need to find stuff. First of all, the hello, how is everybody? Uh, yeah, I need to find stuff. First of all, the hello, how is everybody? Uh, yeah, I need to find stuff. First of all, the hello, how is everybody? Uh, yeah, I need to find stuff. Oops. Okay, so I don't know why this echo is happening. I hope you don't hear that. Oops. Okay, now maybe. Hey, first a confirmation. You hear me? Because I'm a bit new to this. Um, um, Technically, we are live, but it's also with I don't know, like 20-second delay, at least from my side. Let's see. Let's see. Maybe I try another thing, and if not, then it's fine. Now what? Do you hear me? Question mark. Hello? Hey, 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 hey. This is not entirely as expected, but at least there are some, how to say, experiences with this situation as well. Oh, okay. Okay, my microphone says it's working, so I'm going to assume it's working. But then there is this a bit of a latency or delay. But anyway, so I hope you are all good. And yes, so the plan is the following. So that, well, first of all, just wanted to try out this, I don't know even how to call it. Excellent. Thank you, George, for the confirmation that you can hear me. That's good. So, yes, so one thing is there is a bit of a delay, which is coming from the probably software or hardware or internet speed. I don't know, but anyway. So the plan is the following. Just to I just wanted to try out how is this thing working with the live streaming and so on. And the other one is yeah. So basically that was the whole reason. But as for the content. So then I thought that it will be an opportunity if, well, somebody wants to ask something or suggest something, or just to have a little chat. That's the a primary goal of the come on, I cannot call this meeting. It's a just live stream, and the other one is so that there is some kind of a content that is kind of related to genomics, then I thought we could do some kind of well, look at some papers or abstracts or something like that. So not really reading them, because then, then it would be maybe a bit boring for you to see me staring at the screen and reading. Although, well, I will share the screen, so you will see the same thing I see. But still, perhaps rather than spending too much time on a single paper or single resource, I thought we could check on some papers and see what's new. Because to be very honest, I mean, there is a lot of things to do, and there is always the kind of catching up on papers is always somehow, let's say, not the first priority during the day, and then it's then it's well, kind of delayed all the time. So so anyway, I thought this could be some kind of just a way to spend some time, and then just basically waiting, or just if there are some questions being generated or so on in the chat, or just, well, have a bit of time to looking at papers and abstracts related to genomics, and even more precisely genomics of diversity. Yes, and also this is a kind of a sneak peek for you, that how I sound when I record all these videos, because the thing is that so there is a lot of parts that are cut out from the videos that actually make it to the web, or make it to the YouTube. So it's generally a lot of trying to explain things more or less like this, and there is a lot of pauses in between, and yes. So in this respect, this medium of live streaming is quite different, because well, technically or practically also this will also appear in the YouTube at the end, but it will be in an uncut form. So well, there is also a bit of a sneak peek for you how normally the recordings look like. So I have the chat in front of me, or near me, to be very precise. And since there is nothing new there, so we could move on and see what we have. And there is this very elaborate transition. With the Google Scholar. Excellent. So now there is a question. Anybody has any favorite in terms of species or approach? Okay. So there is a question. Quick question about the VARLD while searching for selection signature. Is it necessary to do it per chromosome? Yes, because I mean, generally the VARLD works on a chromosomal basis. So it just, you need to do it per chromosome and then see what is there, because otherwise it won't work. I think there is a kind of an implemented setting or something that looks at the maximum and minimum values and of the SNPs. And if you would do it in a whole chromosome, then there would be many maximum and minimum values, because of course all the chromosomes are different in size, and there are always the base pair positions are reset at the beginning of the chromosome. So yes, that is necessary. Similar question. So the plotting for the VARLD. So in the video that I produced. So there are the plots which are provided by the authors that are per chromosome basis. But then what you can do, of course, if you merge all these files, then you can also do it with for the whole chromosome. So plotting is not necessary per chromosome. Well, you can do it for the whole genome, for a chromosome, or for the specific region of the chromosome that you want to be highlighted. With the plotting, you have absolute freedom. With the analysis, not, because this is just how the VARLD, this specific VARLD software is set up. Of course, there might be other software that is possible to do it with the entire genome, but if we speak about the VARLD software itself, then per chromosome. Good. So, what shall we do here? Some kind of a search on genomic diversity. I mean, cattle is, nah. Oh, it's too mainstream. So let's go some sheep. Sheep is good. If you have other suggestion or even a specific paper, it can be also your own paper, then just let me know. Okay, so let's say we start wide genomic diversity. Any good suggestion? Oh, in forestries. I am too tempted about the trees. Let's see what it is. Although I think the tree genomics is very different because of the size of the genome. Apparently is just huge. Okay, let's see. I mean, we are getting into a very different direction now that I was expecting, but yeah. Anyway, okay. So deal with the linkage disequilibrium in less than. Importantly, in many species, linkage within genes. Within genes declines with less than 10 to the base. Okay. Interesting. Yeah, but maybe something more lively. Yeah, so I have a few viewers. So if you also have any, well, unfortunately, I don't see who you are. But I know you are here. So if you have any question or comment, then or paper suggestion, then just hop into the chat and let us know. But yeah, okay, now let's see something else than the forestries, which is certainly fine. But let's go with the sheep. Although, yeah, I always forget that. So the viewership of the channel is more than animal or livestock genomics. So sorry for my maybe too much favoring of a certain group of species. So if you have anything else, then of course, yeah, we're happy to look at that. Okay, chat. Question. I would like to know if a SNP chip commercially available today are fit to be used within species or some modifications are needed for some breeds. Yeah, good question. Yes, so the commercial SNP chips. So Okay, so a bit longer story, which is in cattle. So the first, like this really big chip was or is still the 50K SNP chip, version 1. That was, I think, primarily developed having towering cattle in mind, and it worked very well in the Holstein population and perhaps some other large populations, also reasonably well in other towering populations. But if you tried out that particular SNP chip, the very same one that worked very well in the Holstein population, in a Bos indicus population, any Bos indicus or zebu cattle, then you found out that, I don't know, 10 or 20,000 of SNPs are basically unusable because they were genotyped, but the minor allele frequency was close to 0. And yes, so this was then recognized, and in the future versions of the SNP chips also corrected. So later, I think the newer version, I think we are at the version 3 now or something like that, for the 50K SNP chip works reasonably well also in Bos indicus. And that's one thing. Also, there is the high-density SNP chip that was working very well from the beginning in all populations. And nowadays, there is also a Bos indicus specialized SNP chip. So if you are very interested in the Bos indicus population, then you can genotype them using this very specific SNP chip. Now, this was also just an example of the kind of an event or the kind of a situation that happens. The name is ascertainment bias. So this is, of course, well, as I mentioned, the example was in cattle, but it could be, kind of extrapolated or kind of more generalized to any population. So the thing is that the SNP chips generally work within species. So if a SNP chip is developed for, I don't know, I want to say something else than a livestock species, but I don't really have, and I'm honestly not too knowledgeable about the plants and others. So, but let's say some other livestock species in sheep. Well, we have a sheep on screen. So generally, it works in all sheep species, but it works somehow better in the species where, or sorry, in the breeds where it was developed or which were considered in the chip development. And for the others, also works, but perhaps not as much, or they could be a bit of differences. So it really depends on how far is this other species, or sorry, I keep mixing up the terms. How far is this other breed from the overall species where it was developed? For example, actually, a sheep is an unexpectedly good example because we have a commercial sheep, and so there are other these wild sheep and all the others like mountain sheep and all these I would call them different species even. Well, I'm again a bit lost in terms of a terminology, or my reference to them as different species might not be totally correct, but they are further away from the population where it was developed. So if you use the commercial SNP chip on them, that might not work very well. So it might work reasonably well, but also it might not work too well. So it's really might not be the best solution. If you want it to work very well, or if you have an entirely new species that you want to genotype, you need to develop a SNP chip for them, or use other methods of genotyping. for example, what you could do is, I give another example from livestock. So there is this cattle chip, and there were, people tried to use this cattle chip on the deer, on the red deer, or farm, because deer is also a farmed deer. So basically, it's kind of a wild animal, but also it's a farmed animal, and it's like, commercially very, very interesting. And yeah, it's good to genotype. So at the beginning, so there was nothing available, and people thought that it's like, well, let's try to use the cattle chip, 50K, and that didn't work out very well, because from the 50,000 SNPs, about 2,000 or 3,000 were actually genotyped. So there was a huge number of SNPs that were not genotyped at all, and many of them which were genotyped had just the horrible kind of minor allele frequency, so they were also useless. So at the end, I don't know how many, but a few hundred SNPs were really usable, which is, I mean, at that point you also kind of pose the question how much I believe these 500 SNPs, they were actually genotyped, if I had to throw away more than, I don't know, 50,000 other SNPs. I mean, that is like, so then for that, yeah, so of course you can genotype the deer as well, but not with the cattle chip. So either you need to develop a specific deer chip, or need to sequence them, or there is also some other methods. For example, the so-called genotyping genotyping by sequencing, which is well, I don't have a lot of experience with this, but apparently is also a good possibility. So I think that there are the analysis of those data is a bit different from the SNP chip data, but yeah, well, this is also a possibility if, for example, you are in a situation that with a species that is not not very mainstream, so you don't have a chip, you don't want to sequence for any reason, so genotyping by sequencing might be a okay solution. Or nowadays there is also a I don't know, a relatively new thing which I heard about more in the last months when there was this so there were two conferences back to back in September this year. The EAP, in Davos, Switzerland. So that was there, and then afterwards I was also at the Animal Science Days, which was held in Gödöllő, Hungary, near Budapest, and in both places. So there was kind of talk about a so-called scheme sequencing. So that would be something like a low coverage sequencing that does something. Well, again, I don't have any experience, so I cannot tell you if it's good or bad, but seems to be there. So that is might be another possibility if you are interested in a species that is not very mainstream. Or of course, if you have a mainstream species, also still you can use the both genotyping by sequencing or scheme sequencing or any other method. So you're not restricted at all. Okay, so just to wrap up this question, yeah, generally you need it within the species. And yeah, so there is also a comment that the wild mouflons ancestors of the current domestic sheep. So yeah, for example, well, again, I don't know how would this work, that if you would use a sheep chip on the mouflons. Probably it will work to some degree, but maybe not as good as for something else. So yeah, we'll see. That is yeah, but good question. I like that. Happy to hear Gadala recently graduated from the university there. Ah, hey. Yes, yeah, it's a good place. Actually, also they have an impressive campus and like a main building. I liked it very much. And also the place is well relatively small, but not as small. I think it's the ideal place. Cool. Yes. So genomic diversity in sheep. Just keep the questions coming. By the way, so the papers are just a distraction for the quiet moment. So, and I also try to get some water. Excellent. I have some note here for later. Good. So let's see from the last 5 years. Is there a difference between selective sweeps and selection signatures? No. To me, or in my interpretation, this is just synonyms. Well, so it's just 2 words or 2 expressions for the same. Yes, both of them are the same. Yeah, sorry, there is a bit of a lag. I think next time I will do a bit of a different setting. Yeah, but so that is there is no such lag in the. I don't know who these people are, but they have quite a bit of a screen time. Screen time for their papers, which is of course good. Visualization of runs of homozygosity in R. So that is depends what you want to visualize. So the segments. So there for that. So these runs of homozygosity is something that I haven't got around on the channel yet. But so in R, that's actually in tidyverse, so there is a, I don't know, stripes or well, now I don't know which one is that, but there is a neat little script that yeah, you can do depending on what you want to do, but I assume you want to those kind of stripes that kind of visualize if there is a run or there is no run. Yeah, well, there it is possible, but I don't have it in mind right now that which one. But so the one of the geom stripe or something similar, and then you have to add the beginning and the end of the run, and this kind of puts it up. But there is also. Actually, this is something that I also wanted to check out for myself, because I think even in one of our publications or more, so that is about CNVs on generally on the genome, and our PhD student was doing that, including visualization, and there is a neat little graph that actually has the whole genome with all the chromosomes in a relatively compact manner. Also, the sizes of the chromosomes are correctly shown and everything, and there is on the chromosomes there are stripes of, well, in this case CNVs, but still, yeah. So this is something I also need to check out for myself. Can we use machine learning methods in detecting selection signatures? Definitely yes. I don't know how, so I don't know. I'm not really a machine learning person in general, but I for sure know that it is possible to do that. Actually, we are now, yeah, well, of course, there is always looking at the future and so on. So we might do something with machine learning and selection signatures, but this is just very much in a future, so it's too early to talk about it right now. But from that reason, I definitely know that it's possible. But I cannot. But this is everything I know about that. So what approach or software or anything like that? Honestly, I have no idea right now. Well, hopefully I will gain some knowledge as well, and then I will also put it on the YouTube channel as well. So that is the. So yeah, actually, one more stuff that I wanted to do or is in plan to do is the kind of the 1,000 subscriber thank you video, which is yeah, well, that is also will be done, and there I might detail some of the perhaps more personal stuff on the, well, not very personal, but I mean something along the lines of my what I have done in the years, on the past years, and yeah, so from there you would see that yeah, so there is these things that we speak about now also in the channel, they are just kind of gradually coming with the things, and there is also a lot of things that I still need to improve on. So, and that one of them is the machine learning stuff. So, well, actually, I find it personally very interesting, and also there is a lot of applications for the yeah, for in general for the in genomics. So it's kind of good, and also it's kind of fancy to be honest. So why not? Okay, so I've talked about the CNVs in one of my videos. Maybe I just put back on this. So what it is by passing. Could you elaborate how useful they are in the data analysis and how to visualize them? I mean, yeah, so the CNVs are copy number variations, meaning that, so these are mostly insertions or deletions or duplications. So basically, or in that manner. So it's something that is a part of the genome that is getting shorter or longer. So well, it's actually in the name that there are several copies of the same region, or there is a reduction of number of copies that would be a deletion. Now, CNVs in general are detectable by using whole genome sequence data, because there you can or have the means to detect or kind of look at all the nucleotides, and you could see if there is a certain region is being deleted or not, or kind of duplicated also. With SNPs in general, this is a bit more tricky, because just the SNPs are just single point mutations. So, and there is a lot of place in between them that is that you don't see. And if the deletion or even the duplication or anything like that is very small in between the SNPs, you just don't see it at all. If we speak about large CNVs in general, whatever direction, then you could actually detect them somehow with SNPs. And for this, it's very useful to have and that perhaps this was because in general, just with the PLINK data as it is, you cannot do, or I don't know, but in my knowledge, you cannot do analysis of CNVs. But what you can do is if you have the final reports from the file from the place where you got the SNP genotypes, then you actually have much more columns, and two of these columns are very important in this respect, and that is the B allele frequency and the no, I forgot the other one. But anyway, so there is a B allele frequency. I had it before, but I forgot which is the other one. But anyway, so there are this stuff in the final reports that you could use for a log-R ratio. Thank you. Yeah, good to have helpful people in the chat. Yes, so basically with these ones you could also analyze CNVs with the SNP data. I mean, and with that, so basically it's actually quite straightforward. Actually, I might try to do that in one of the videos, because basically what you need to do is kind of just plot these two values, and you would see kind of a decrease or increase in terms of these values in a certain spot or in a certain region, and that is then an indication of a copy number variation. So that is how you basically analyze that. And so there is, of course, software, and visualization is also, yeah. Well, I don't know if there are packages, but there might be also packages for that. But for sure, it's kind of with the tidyverse, or you could do many things. And actually, this was also the place where I mentioned that there was this pretty nice map of the genome where the SNPs or the CNVs in this case were visualized. What is a problem many times is, and I tell this one to many people, I just, if you meet me in real life and we talk about genotyping, then talking about genotyping in general, and one of the things I surely would tell you is that what you do with the final reports. And to my surprise, many people are just throwing them away, or just they don't know where they are. So they just don't care about them anymore, because they have the PLINK data, and basically that could be used for the purpose they want. Which is fine, of course, because from the PLINK data you can kind of get out a lot, but just throwing the final reports away, or kind of not caring about them is a big, I mean, it's not a problem, but it's a missed opportunity. I would talk about it, because you could have these things. You can analyze more stuff than just with the genotype data. Also, if you have the final report, then you are much more flexible in terms of having your data connected with other data sets, because what you can find also from the internet or open access resources or from your colleagues, they have some kind of a data, but let's say that they have a top coding or a AB coding, and you have a forward coding. So then you cannot directly merge it, and there is like kind of trying to translate it to one to another. It's a bit cumbersome, or there is always a possibility of the mistakes and so on. So, but if you have the final report, no problem. You just extract a different column, and then you can straight away merge with the data of your colleague or open access or anything like that. So for that reason, having the final reports is very, very essential. And nowadays also, there is also not a problem in terms of space or storage space, because this is text data, so you can zip it together and just have it somewhere, in a backup space. And yeah, but you don't need it all the time, and when you need it, you have it. So this is really, really a good one. And so there is a Satish. It says handy CNV recently published. You can use that. We can use that to plot CNV data. Really? I will check it out right away. So, the CNV. Oh, this is from my. Well, not my. Okay. Let's see. Maybe I put this one on the screen as well. Okay. Oh. In R, nevertheless. Summary annotation. Comparison visualization. Oh, this is really, really neat. Good, thank you, Satish. I hope I pronounce your name correctly. On GitHub. Looks nice. A lot of steps. Oh, and also here there are some. It seems like an LD plot, which actually I was also after. Is it better to use high-density SNP data or whole genome sequence data for better understanding the role of variants in the genome? If so, how much depth we have to sequence, suppose in cattle? So this handy CNV is very handy. We will check out that. Yeah, so for your question, depends what your question is, honestly. Because if you are interested in like a population-wide characteristics, then even going lower than 50 or HD is also fine. But but your question is specifically on the role of variants in the genome. That's an interesting question. My immediate personal opinion is the following. So without thinking about it too much, if you want to specifically localize where certain variants might be, or if you're not really interested in the alleles themselves, but you're fine with losing some resolution in the favor of more genotypes, or hundreds of genotypes or thousands of genotypes, then I would go for the HD, honestly, because you just can have more data, and HD is relatively, relatively dense, and you can do quite a lot of stuff with it. Still, in cattle, on average, you have still like 3,000 or something like that nucleotides between each of the two SNPs on average. So you still, you still miss a lot. So if you are interested in some very, very specific region for them, some very specific trait, you want to do it as you need to really, or want to really understand what's going on, then I think the sequence data is better in this case. So if you are really focused and you have a clear goal that what alleles you want to target, what specific alleles what you want to target, and why. The depth, yeah, I could say that the more the better, but that is not an answer. Yeah, so again, with the note that I am not working too much in or almost at all right now with the whole genome sequence data, but my personal what I gather from various sources that like a 20x would be like a minimum that go for, and if you want to, 20x, it's a bit hard to say because this is also somehow when the people say that there is 20x on average, that can be a bit misleading because then it could be that some animals are or some individuals are much less than 20 and some are more, so you have an average of 20. So I mean, no, I'm not. You could probably see that I'm not really feeling comfortable answering this question. Around 20 should be fine, but if you want something very specific, then probably more. Sorry, this is no. Probably there are better people to answer this question on the X coverage than me. But yeah, definitely don't settle. That what I can tell you. I mean, yes. So you could do it with a 10 or something, but so I would say you get results. but if your goal is really to understand something, then you have to be sure what's going on. So then you need to have like a higher X, and the higher X for me for a study that would kind of have the goal to understand the nature of the trait, then would start somewhere at 20x for me. Yeah, if you have like a population-wide study on if your goal is to extract I don't know, population-wide SNPs, something for a diversity-related study, you can go I think even lower because, well, for the SNPs it's fine, but if you very want to do a specific gene or specific region for a very specific purpose, you need high X coverage. Okay. We have some reservations on the use of genome data for selection of especially small ruminants due to the cost of genotyping one animal compared to the value of the one chip compared to the value of the animal. What is your opinion? Yes. So actually, this is a serious issue, honestly, especially when it comes to the fabled genomic selection, because yeah. So exactly as you mentioned, George, that if there is the value of an animal is not so much, and you basically the chip costs or the genotyping costs is a serious proportion of the value of the animal, then why should I do it as a breeder? It doesn't bring me double income from that particular animal. So yes, so this is one way to look at it. The other one is that fortunately the genotyping costs are lower nowadays than used to be. So it's this kind of disproportion is kind of going away. So I think also previously the genomic selection or in general actually the genotyping was done in cattle because the price of the animal is high, and also there's a long lifetime and so on, and you need a lot to invest, especially if we talk about dairy. You need a lot of investment before the animal starts to produce. So there you actually can gain a lot by investing, I don't know, 100 euros or whatever was the price then. But if we talk about sheep, pig, goats, no, then the price of the animal is not so big, and also the reproduction rate is much higher. So basically, you can for that price, you know, you can invest in more animals. Yeah, so this is from this reason, this is a really a question. On the other hand, and I think this is the place where the differences between the small breeds and the large breeds, or no, sorry, rephrase. Small breeds, I mean, is small breeds in population size, and the large breeds meaning like a commercial breed. So more specifically, differences between the large breeds and small breeds and commercial breeds come into play because behind the commercial breeds, there is probably a breeding organization and people who kind of willing to invest into the, into genotyping, even if it doesn't give immediate kind of payouts. So that's why I think, especially in these larger breeds, in terms of larger, more commercial breeds, you could see actually the genotyping flourishing also nowadays, and especially if these places where the genotyping are companies or just industry, then they have really a kind of they get value out of it on competing on the market and everything. So that's why I think also what you see now is for example, in the pig breeding, there is no question nowadays that genotyping is being done in a wide scale, so the results are being implemented. Also for the genomic selection purpose. For the smaller, let's say more native breeds, or some I am missing the words. Indigenous breeds, for example, where there is hardly enough breeding going on, or organized breeding going on, perhaps the genotyping is not the first thing that you should do. So then you should invest more in organization or in the recording and so on. So that is in the small breeds or in indigenous breeds much more important than the genotyping. So having appropriate pedigrees, recording of the the production, all this stuff. Also, well, again, something that I'm absolutely not familiar with, but having these it's not supply chains, but the market. There's something with access to the market, and there is a phrase for that. It's not supply chain. Value chain. Yes, value chains. So for a long time I didn't understand what value chains are, but so these actually value chains in the small breeds are much more important than genotyping. Yeah, of course, these all things are easier said than done. So they require quite a bit of effort, and in between, so maybe. So that is the thing to go on. But on the other hand, also is, well, the breeding organizations or the breeders is the one side, but I believe, or this is also my opinion, that especially in these small breeds or the smaller breeds, non-commercial indigenous breeds, that frankly they have next to zero chance of being worldwide leaders in their kind of category of production in sheep or goat or anything like that. So for these ones also the governmental kind of support is also would be good, or kind of so. I mean, what I want to say that is well, this is again a topic that is very hard to comment on, but yeah, so maybe I'm overcomplicating it anyway, but no, to me, just to kind of summarize and wrap up the whole thing. So especially on this in this let's say small ruminants or some this less like less valuable. Now again going into the wrong direction. Yeah, so let's say in small ruminants, the genotyping is for sure less frequent, but it's useful for from some reasons. For example, if you want to find out about the genomic diversity and something like that. So from this kind of angle, it's fine to have genotypes. But then again, there is a question if breeders should pay for these genotypes if the purpose is just to see how the breed is doing, or you know, this kind of a diversity-related studies, which are generally not that useful for the breeders. The information, of course, is useful, but then it doesn't increase the value of their animals per se. So this is a bit of an issue. But yeah, so that is perhaps I would close it like that. And yeah, and I with also with the saying that I hope that the prices will go even lower, and then there will be some general effort to have at least a representative sample from every species and every breed from every species, which would be actually nowadays quite feasible. So, but then of course again somebody has to pay for that, so that is also not so easy. Again, other question: any classification of selection signatures into generations like first, second, and third? Which method of selection signature statistics are preferred in identifying selection signatures? Okay. So this selection signature classification. So in general, so there is, I cannot say that there is a preferred method. So they are, and actually at some point I wanted to make a video on this as well, because it's just a kind of a nice piece of information. So there is a bunch of selection signature methods that is usable, or kind of method itself is usable if you want to detect selection signatures within breeds. So if you have a single breed and you want to detect a selection signature there, that's one thing. And there is another group of methods that is used when you want to detect selection signatures between two breeds. So the two examples, so there are much more, of course, and actually at some point what I wanted to do is kind of have an example for each of these methods. But yeah, so right now I went with the two that I'm using quite often, and the example would be actually no, I'm wrong. I wanted to say that FST is within breed, but it's for that you also need to compare two populations. So anyway, so FST and VARLD, so both of them are actually between two breeds, but also there are possibilities of within breed that you know, so that also mostly based on some aspect of homozygosity. So that the regions are being more homozygous than expected by chance. And so with these kind of methods are also you can find out or localize some selection signatures within breed. But there is a kind of a nice tree of these methods that yeah, well, could be used. But there is no such thing as preferred or best or anything like that. So there are options, and then actually there are some methods, or so there's a number of options, and then you could apply more than one to the same data set and hoping that you get out the same results or same regions. Well, now often you would find that they are not matching. The results are not matching all the time, and one method finds, let's say, one set of results, and the other method finds other set of results, and maybe partially overlapping. So, and then, and then of course there is a question: what should you do now? So that is always a tough one. But also, what you could do is combine some of these methods. So these are so-called blended methods that that you could combine more than one method, and then some with kind of a joint score or something like that. You have maybe a better answer. But even then, I would not claim that that kind of a blended method or something is the best you can use. When you detect selection signature between two or more breeds, how will you tell that the signal belongs to breed A, B, or C? Okay, so so one thing is, if you want to do selection signatures, then probably you should do two breeds. So if you have three breeds, you can do like pairwise or combine, but actually, so you can also, of course, in one study or paper or something, you can have more than two breeds. But when you're comparing, probably you need to do a pairwise, or actually, which is being done in one of our upcoming papers. There were some animals that were grouped together because they were from similar breed. So you can actually, or I hope you can do that. This paper will go under review, so we'll see. Maybe the reviewers will have another opinion. But how you decide where the signature belongs is, so all of these signatures are based on some kind of a metric. It's basically, if you compare two breeds, there is some kind of a difference in that particular region, which is indicated as signature, because otherwise it will be just, you know, not special at all. But because there is some kind of a difference, then it's kind of pops up as a significant signature. Now, depending on what your method was looking at, then you could, for example, if the method was based on some measure of homozygosity, then looking at these exact regions of these two species or breeds or whatever you compare, you will probably find that one of the species or one of the breeds is much more homozygous in this region than the other one. Or for example, in VARLD, if you do this with VARLD, and you would find that there is a much higher was that linkage disequilibrium or pairwise linkage disequilibrium in one place than in the other. So in one breed than in the other breed. Actually, now I'm thinking, because yes, actually exactly this topic will be in the video next week or the week after. Actually, it's already done. So I'm actually discussing this exact topic there. Well, not very long in a long form, but it's in a also just showing the scripts and everything. But the thing is that, for example, also here, what you could find that one of the breeds has a much higher pairwise linkage disequilibrium in this exact region compared to the other breed in this other exact region. So then you could argue that well, the selection signature itself is, if you think about what it is, it's the signature is just shows that there is some kind of an underlying gene, most likely, well, it should be a gene that is under selection, either natural selection or artificial selection. And what you see, the SNPs around or the signature or kind of popping up on the graph is just the visuals of indicating that something is there. So yes, so and this selections, this gene actually is because of the, well, just by definition, the linkage disequilibrium. It's actually kind of pulls or kind of it's not being inherited as a standalone, so not a gene by gene basis, but kind of a segment. And then if there is a selection signature, so then you assume that this segment also with the SNPs and nucleotides around it is more conserved or more stable because of this gene being there and being selected for. So it's basically the recombination doesn't chop up the genome in a random way, but these exact haplotypes or exact pieces of the genome are being inherited, and they are much more widespread in the population than they would be just in a case of a random part of the genome. So from this you could assume or that wherever you see higher homozygosity or higher linkage disequilibrium within the breed, there is that is the breed from the two which is where the signature actually belongs to, and which would kind of drive this selection signature in some way. So there is in that breed is the selection kind of being realized for that particular part of the genome. Of course, there could be a different signature in the same analysis even, but it could be also for the other breed. So that is, I think this is a case by case and signature by signature basis. Good. Well, I hope that was an okay thing. And yes, what we could do right now is basically, well, I don't think we there was this very optimistic plan of going through some papers or abstracts, but I don't think it will be happening anyway. But on the other hand, I was very happy to have some chat with you guys, and I don't think we would go to the papers right now anyway. So well, definitely. So this video will be, or it's live now, but it will be also on the channel. So it I think as a normal video. So you can also check it back, and it will be in unedited form. So my long pauses and kind of rephrasing stuff and all that stuff is still there. So maybe you can skip over that or kind of watch it in a higher speed. But otherwise, yes. So I think we would wrap up things here. So there is a final question. My data had a lot of negative inbreeding coefficients. Is this normal? Depending on which, so you use the FIS, because there is for the inbreeding you could also use different metrics. And if you use I think it's FIS, then it's fine, because then there is the ranges between -1 and +1. So that is it has a meaning, so that's fine. If you used runs of homozygosity or kind of proportion of genome being in runs of homozygosity to the whole genome, that should not be negative. So that is depending on that, but that would be also a well, not a computational problem, but some kind of a problem in the script or something like that. So if it's this one of these rights, oh yes, the head, yes, then that one is that one is one of the rights indexes. I think FIS or something like that. So you check, but that one is valid, or the negative values are okay, unless they are in the range of -1 to +1, but then you need to look at the interpretation. No problem, Satish, anytime. And yes, so then we wrap now, because I mean, I'm not worried about going over time, but there is always good to set some limits. And anyway, so we will do, yeah, so finish now. So as I mentioned, everything is online still, and at some point we can do another one. So it's maybe not next week, but at some point we could do a different round. I don't know, perhaps same way, similar way, or change something. Actually, what I wanted also to ask about is, so there will be this video, and also then you could put down in the comments, and this is for everybody who's ever watching this video. So just put down in the comments if you liked this format. That's one thing, and the other one is what else could be discussed, because it's in this. Well, there's live stream. It could be used for various purposes and opportunities. Well, there could be a set of questions, or I don't know. So I don't want to give examples, but if you have some good idea what could be done, during this time, or we can analyze something, or at some point I was thinking that trying to visualize some data sets or something like that could be also an option. But then this is a bit of a tricky one, because I mean, I'm not afraid to show that, but it's you would probably see that the visualization or just a new analysis of anything, it's very, very cumbersome. So that would be me looking at Google quite a bit or something. But on the other hand, maybe we could all look at Google together and solve problems in a joint way. So then perhaps it's even quicker than usual. Anyway, so let me know what other topics you would prefer to have in such a live stream, and at some point we will return to this, and we'll see. And we could do something else or something similar as you want. Okay, so then now I think this is really the end. Thank you very much for being here. And yes, some other time we see each other live. Also, perhaps at some conferences, because, well, if you are especially from the animal science, then the animal science world is not so big. So we probably meet at some conferences. And otherwise, well, online or through the YouTube videos. So thank you very much again, and thank you for being here, and just the conventional or the usual wish from me for you to have a very nice day, and thank you again. Hey.